Last week, we mainly focused on the problem of finding of the dimension of any divisor A, and particularly we consider the upper and lower bound for this quantity. And we have observed that lower bound indeed is independent of the choice of the divisor and only depends on the function field, given function field f. And again, thanks to this lower bound, we will be able to introduce the most important invariant, algebraic invariant, what is called genus of a function field, as a difference between the degree and the dimension of the divisors for all divisors A, and including +1. And we have observed that this is an integer and this is a positive integer, non-negative integer, because by the definition we know that this quantity is bigger than always bigger than or equal to this one. And in particular, if you consider the zero divisor, degree 0 minus L of 0 plus 1 gives us the desired lower bound for the genus. And conversely, if you consider the problems, for instance, if we consider a function field with given genus, for any divisor, again by the definition, we can easily observe that the dimension always is bounded below degree A plus 1 minus G in this case. And we also stated that if degree is sufficiently large, we still didn't explain it yet, but in this case, we will be able to compute the dimension of a divisor exactly. So again, regarding the same question, in this lecture, we will explain what does sufficiently large mean, or in general, can we compute the dimension of a divisor. And the most important theorem in algebraic function fields will be an answer for this. And in this case, we suppose that we are given a function field. And this theorem tells us that there exists an integer and a divisor W such that for all divisors A, its dimension is equal to its degree plus 1 minus G plus L of W minus A. So in this case, actually, we can view this dimension of the divisor W minus A as the difference between this quantity, because for any divisor, if L of A is bigger than or equal to this one, so that means we need an additional term here, and this L of omega minus 1 will be the desired additional term. And moreover, G and W are uniquely determined by the function field, so they only depends on the function field, and indeed this equality works for all divisors. And if we suppose that there exists another integer, let me call it that G0, and if another divisor W0 that gives us this equality for all divisors, then we will see that indeed this integer is unique and this divisor is unique up to equivalence. So G and W are uniquely determined in the following sense. If there exists another integer and divisor such that, again, for all divisors if we get the equality in star, then G is equal to G0 and the divisor W is equivalent to divisor 0. So actually this is quite a strong theorem because we get this equality independent of the choice of the divisor. It works for any divisor. And the advantage of the algebraic function field will be that actually we will be able to prove this theorem without using any fancy terms from the algebraic geometry. However, the disadvantage, it will require the proof, particularly to see the existence of G. And indeed, this G will be the same thing with the genus that we defined here. And to see the existence of such a divisor, we will need more advanced tools, and probably we will see them a month later. But for the moment, we want to focus on the computation aspects. Okay, we just believe that such an integer and such a divisor exist. And what can we say about the dimension of the Riemann-Roch spaces? And for this purpose, we only, at the moment, we only prove the uniqueness of this integer and the divisor, and then we will focus on the consequences. So let me suppose that, show the uniqueness. We have pairs GW and G0W that satisfies this equality. For any divisor A. Then our first claim will be that G is equal to G0, and to see that if this equality holds for any divisors, we may consider a divisor A whose degree is bigger than the degree of such divisors W and W0. And if this holds, and of course this equality holds for also for this divisor. And if we consider the equation of the L of A and degree A plus 1 minus G L of W minus A. So by the assumption, the divisor W minus A has negative degree. So the corresponding A space has 0 dimension. And on the other hand, if we also have this equality for the integer G0 and for the divisor W0, again by the assumption, the dimension of W0 minus A is going to be 0. And the dimension of L of A is equal to degree A plus 1 minus G0. And thanks to this equality, we will see that indeed such two integers are the same. And now we want to see that such two divisors are unique up to equivalence. So in order to see that, first let me observe This is our claim. So first, let me observe that indeed they have the same dimension. And to see that, you particularly consider the zero divisor and consider the equal to star. So that means L of 0, degree 0 plus 1 minus G, L of W minus 0, and on the other end, this also holds for W0. And as we have seen, in the G0 and the G are the same. And we know the dimension of the zero divisor, which is 1. And this shows us indeed L of W is equal to G, and L of W0 is equal to G0. Indeed, this is also G. This will be also important information for such a divisor W. And our second claim will be that, okay, we have observed that they have the same dimension, and now we will observe that they have the same degree. And for this purpose, we consider divisor W and write the definition of the equation we consider in the main theorem. And similarly, we will also consider W0. This is degree of W0 plus 1, G0, L, W0 minus W0. So again, this is going to be zero divisor. It is dimension 1. And we have observed that such a divisors can only have dimension G. And from these two equalities, indeed, we see that degree of W is equal to 2G minus 2, and degree of W0 is equal to 2G0 minus 2. So we can also see that they have the same degree. And finally, to see that they are equivalent, we consider the divisor is the difference of this such two divisors W and W0, because we know that in this case, if they have the same degree, this divisor has degree 0. And if we are able to see that it has dimension 1, then we can conclude that this is principal, and we can see the equivalence. And for this purpose, again, let me consider the equality in the statement of the Riemann-Roch theorem. And since this is degree 0 divisor, we get they have the same degree, so the degree of the difference will be 0 plus 1 minus G L of W0. And since L of W0 is equal to G, it has dimension 1. And by corollary 1.4.12, particularly part C, since it has degree 0 and is of dimension 1, we know that omega minus W minus W0 is principal. And this shows the equivalence, actually uniqueness, up to equivalence. And indeed, by depending on the statement of this theorem, we will redefine the genus, but unfortunately, we still won't see for a while. Indeed, it is the same integer we consider here. We will see it later. And the last but the least, such a divisor that satisfies Riemann-Roch theorem, that gives us the equality in the Riemann-Roch theorem, will be called a canonical divisor of f over k. And these will be the notions supporting each other if you want to find one of the and the other. And as we have observed when we do the theory, when we consider the proof of this statement, when we consider the uniqueness, at least we know that such a divisor is of dimension G, and its degree is 2G minus 2. And in the next video, indeed, we will see that all divisors can be characterized with respect to this property. I mean, conversely, we will see that if a divisor is of dimension G and is of degree 2G minus 2, indeed, it will give us a canonical divisor. So that means it will be equivalent to a canonical divisor.